When in doubt, some forces. We want to look at a couple of examples of how to apply Newton's second law to solve force problems. Our procedure's going to be the same every time, even though problems can be different. We're always going to start with a free body diagram. We're going to try to look at what forces are present in the situation. Then we're going to write an equation using Newton's second law to try to solve for any forces that we don't know. Any object gets its own free body diagram. Remember, we might be interested in the forces, but forces have to act on an object. So we always put the object at the center of our picture and then ask ourselves what's pushing or pulling on the object. Then we start our equations by either saying net force equals mass times acceleration, or net force equals 0 if we're at constant speed or at rest in either the vertical or the horizontal direction. We want to start with a situation where we're in complete equilibrium, both horizontally and vertically. We've got an object that's just hanging there by two strings, string 1, string 2. And what we want to know is what is the tension in the strings in terms of the mass. We're just going to instead of putting a number for the mass, we're just going to let mass be m, because sometimes you've got to work your way through problems just using the variables and using algebra. Turns out m could be anything. So we'll just use m, but in order to make the math simpler and worth looking at, we will use two specific angles. We'll use 40 degrees and 60 degrees. Now, if we follow our procedure, we're going to start by drawing a free body diagram. And our object here is the box, because the ropes push or pull on the box. We've got rope 2 going out this way. We've got rope 1 going out this way, not quite as steep. And then we've got the weight of the box pulling down. And make sure we label all these vectors. Now, since it's a rope, we'll call that T1 for tension and T2. Now, we need to make sure we work our angles into the free body diagram, and that's going to take a little bit of geometry. Now, if I go to my original picture, I kind of draw a line, I kind of superimpose the axes right here, you can see that we've actually got a little triangle. And so if that's 40, that's 90, that's going to make that angle 50. So the vertical angle here is 50, the angle with the x-axis is 40, and you can use either of those two angles. Now, because I did my work prior to shooting the video with these angles, I'm going to go and fill it in, but you could do it either way. It's just going to change which trig you use. But your trig determinations depend on how you set your angles, so it's crucial to get this first step right. So we've got 60, 90, the top angle here is going to be 30, and that's going to make this angle 60 degrees right there. And so we've got all three vectors in our diagram. These are the things that are pushing or pulling on our box. And so we want to make an x column and a y column now. And we always want to start by writing that the net force equals mass times acceleration. Since we're at rest, the acceleration is 0. You always want to start with the simple equations and substitute later. Don't try to dive straight into it. Now, let's also say that the standard up and to the right is positive. Before we can fill in forces underneath F net, we've got to say which direction is positive. In the x direction, we've got to the right. We actually said T2 is our positive force, so that's going to be a little out of order, but you just follow the direction here. T2. Now, because this is diagonal, you've got to use components here. Any diagonal vectors have to be listed with their components. And remember, our shortcut here is to put our pin here and say that the horizontal component of T2 is adjacent. Our pin is adjacent to 60. and so that's going to be a cosine 60. Now since t1 points in the negative direction, it's going to be subtracted here. Now again, if I put my pencil down, horizontally speaking, we can see that that's adjacent to t1, or adjacent to 40 degrees. And so, once again, I'll choose cosine because of it being adjacent. mg doesn't appear in this equation because it's not a horizontal force. None of this, no portion of this vector points left or right. Well, to do some quick algebra here, we can see that t2 cosine of 60 will then equal t1 cosine 40. Now thinking ahead, I'm going to need to solve for one of these in terms of the other. And so I'm going to divide both sides by the cosine of 60. That's a mistake. And we'll see that t2, and by the time you run this through the calculator, is going to equal t1 times 1.53. In the y direction, we want to look at which forces point up and which forces point down. We'll start with the upward forces because that's the positive direction. Now, again, if you remember our vector components, the vertical component of t1 is opposite to that 40-degree angle, so we're going to have to use the sine function. Now this is going to be a plus sign because t2 is also a positive force. And if I use the pencil method to check my trig, once again I see that the vertical component is opposite to the 60 degrees. So it's going to be t2 sine 60. And then the weight, mg, is going to be subtracted because that points in the downward or negative direction. And that all equals 0. Well, at this point we're finished with the physics, and now it's just time to do a little math. Simplifying this, we get t1 times 0.64 plus t2 is 0.866. And I'll bring the mg to the other side here so I can work with tension over here and givens and known constants over here. Now instead of writing t2, all of this is the same thing as t2. Now I've got to bring down the 0.866 because this stuff is just a substitution for t2, and mg comes down. So what I can do here is just do a little bit of order of operations, multiply first, and then combine similar terms, and that's going to turn into t1 times 1.96 equals mg, and I'll go ahead and put in the 9.8. So if I divide both sides by 1.96, t1 is going to equal 5 times the mass in newtons. Again, there's no real units over here. It's just because that I've been dividing and doing the algebra that you kind of have to put the units back in yourself if you had the mass there. I can plug that in right here. T2 would equal 5m times 1.53. T2 is 7.7m. So if the mass was 10 kilograms, T1 would be 50 newtons, and T2 would be 77 newtons.